Picture the night sky, not as you see it now, but as it should be, filled with the glow of countless stars, billions of suns, each a beacon of light, woven into the fabric of the cosmos. But something's wrong. A vast portion of that light is missing, vanished, as if the universe itself flickered and left behind a gaping darkness. This isn't science fiction. It's one of the most perplexing mysteries astronomers face today, the missing light of a billion suns, and what, against all odds, has taken its place. Think about that for a moment. Light doesn't just disappear, it travels across space for billions of years, carrying the history of the cosmos with it. So when scientists realized that an enormous amount of light, enough to outshine entire galaxies, was simply gone, it sent shockwaves through the world of astronomy. Where did it go? What could possibly swallow that much energy without leaving a trace? The answer, or at least the hunt for it, leads us down a rabbit hole of cosmic oddities: dark matter, black holes, and phenomena so strange they defy our current understanding of physics. This is more than just a puzzle for scientists. It's a story about the limits of human knowledge and the audacity to ask, what if? What if the universe is hiding something in plain sight? What if the darkness isn't empty at all, but teeming with secrets waiting to be uncovered? That's the journey we're embarking on today, a dive into the shadows of space to explore the missing light of a billion suns and the mind-bending possibilities of what might have replaced it. By the end, you'll never look at the night sky the same way again. To understand how light could vanish on such an unimaginable scale, we need to follow its journey through the cosmos. Light travels across space in delicate threads, weaving through galaxies, gas clouds, and cosmic voids over billions of years. Normally, we can calculate exactly how much light should reach us from distant stars, but when astronomers tallied it all up, the numbers didn't match. The universe was glowing far dimmer than it should have been, as if someone had flipped a switch and turned off entire sections of the night sky. So where does the light go? One leading theory points to the universe's hidden architecture: vast, invisible structures we can't see directly, like dark matter. Picture a colossal cosmic sponge, soaking up photons as they pass through. Dark matter doesn't emit or reflect light, but its gravitational pull could bend or trap it, effectively making the light vanish from our observations. Another possibility involves supermassive black holes at the centers of galaxies. These gravitational monsters don't just swallow stars, they might be siphoning off light itself, warping space so severely that photons never escape. But here's where it gets even stranger. Some scientists argue the missing light isn't being absorbed at all, it's being transformed. Quantum physics suggests light could interact with mysterious particles we haven't discovered yet, converting into something entirely undetectable by our telescopes. Imagine pouring water into a sieve only for it to emerge as mist. That's the scale of the mystery we're dealing with. The implications are staggering. If we're missing this much light, what else are we overlooking? Entire chapters of cosmic history could be hidden in plain sight, waiting for the right tools or theories to reveal them. Every time we think we've mapped the universe, it reminds us how much we still don't know, and that's what makes this puzzle so thrilling. Dark matter might be the universe's greatest disappearing act, an invisible thief silently stealing light from the cosmos. Imagine walking through a fog so dense it swallows every beam of light, yet you can't see the fog itself. That's the eerie possibility scientists are grappling with. We know dark matter exists because of its gravitational pull. It bends the path of light from distant galaxies like a cosmic lens, but it refuses to interact with light in any other way. No glow, no reflection, no shadow. It's as if 27% of the universe is made of ghostly scaffolding, and now we're wondering, could this phantom material also be the reason billions of suns seem to flicker out? The math is tantalizing. When researchers calculated how much light should be reaching us from the far edges of the universe, the numbers came up short like a cosmic bank account missing a fortune. Some theorists suggest dark matter particles might have a property we've never detected before, an ability to nudge photons just enough to scatter or absorb them over immense distances. Picture a vast, invisible net stretching across space, its threads so fine they only catch light after it's traveled for billions of years. If true, this wouldn't just explain the missing light, it would mean dark matter shapes the universe in ways we never anticipated, not just with gravity, but by actively sculpting the light we see. But here's the twist: dark matter isn't the only suspect. Another camp of researchers argues that if dark matter were absorbing light, we'd see subtle distortions in the light that does reach us, like heat shimmering over a desert. So far, those fingerprints haven't shown up clearly. That leaves us with two haunting questions. Is dark matter more complex than we thought, capable of hiding its light-stealing tricks? Or is something even stranger at work, a phenomenon we haven't even named yet? What makes this mystery so thrilling is its scale. We're not talking about a handful of dim stars, we're talking about enough missing light to outshine entire galaxy clusters. If dark matter is responsible, it would mean the universe's hidden skeleton is also its greatest illusionist, performing a vanishing act on a stage billions of light years wide. And if it's not dark matter, well, that might be even more exciting, because it would mean there's a whole new chapter of physics waiting to be written, one where the answers lie in the darkness we've yet to understand. Black holes aren't just cosmic vacuum cleaners, they're the ultimate light traps, bending space so severely that not even photons can escape their grasp. At the heart of nearly every galaxy, including our own Milky Way, lurks a supermassive black hole, a gravitational behemoth millions or even billions of times heavier than our Sun. These monsters don't just swallow stars and gas, they consume light itself, creating eerie voids where photons vanish without a trace. If you've ever wondered why black holes appear as Inkai silhouettes against the glow of distant stars, this is why. They're not just dark, they're light thieves on a galactic scale. But here's the puzzle: while black holes are undeniably efficient at trapping light, there's a mismatch in the numbers. Astronomers have catalogued countless supermassive black holes across the universe. Yet when they tally up how much light these objects should be absorbing, the total falls far short of explaining the missing glow from billions of suns. It's like realizing every cookie jar in your neighborhood has been raided, but the crumbs found only account for a fraction of the missing treats. So where's the rest? Recent supercomputer simulations might hold a clue. Scientists have discovered that black holes don't just swallow light in their immediate vicinity. Their gravitational influence stretches much farther than we once thought. Imagine a black hole's pull warping space like a funnel, not just capturing light that ventures too close, but also bending passing photons into spirals they can't escape. These shadow zones could extend for light years around each black hole, effectively erasing far more light from the cosmic ledger than traditional models predicted. Yet even this revelation raises new questions. If black holes are stealthily siphoning off light across such vast distances, why don't we see more evidence of their feeding frenzies? The answer might lie in the quiet ones, dormant black holes that aren't actively devouring matter, and therefore don't emit the telltale X-rays or jets we typically use to spot them. These dormant giants could be lurking undetected, their light trapping shadows invisible to our telescopes until we develop new ways to peer into the darkness. The deeper we dig, the stranger it gets. Some theorists propose that early in the universe's history, black holes may have been even more voracious, growing rapidly and trapping light in ways that left permanent voids in the cosmic background. Others suggest that intermediate-sized black holes, elusive objects heavier than stars but lighter than the supermassive ones, could be hiding in the gaps, collectively accounting for the missing light. What's clear is this: if black holes are the culprits, they're far more cunning than we imagined, not just consuming light but hiding the evidence of their feasts. And if they're not responsible, well, that leaves us staring into an even deeper mystery, one where the universe's missing light points to forces or phenomena we've yet to dream up. Space isn't the pristine void we often imagine. It's more like a vast, shadowy cathedral filled with drifting motes of cosmic dust. These microscopic particles, remnants of ancient stellar explosions and collisions, hang between galaxies like a fine mist. And just as fog on Earth can dim distant streetlights, this intergalactic dust scatters and absorbs starlight, subtly altering what reaches our telescopes. At first glance, it seems like the perfect culprit for the missing light mystery, a natural cosmic filter quietly dimming the universe. But when scientists ran the numbers, the math fell short. Even accounting for all known dust, the amount of missing light is staggering, like trying to explain a blackout with a single burnt-out bulb. So why doesn't dust solve the puzzle? Ordinary space dust made of silicates, carbon, and ice absorbs and re-emits light in predictable ways, leaving behind telltale infrared signatures we can detect. When astronomers scanned the skies for these infrared fingerprints, they found only a fraction of the dust needed to explain the light deficit. It's as if we're searching for a smoke screen but only finding wispy tendrils. This gap led to a tantalizing question. What if there's another kind of dust out there, one that doesn't play by the usual rules? Enter the idea of dark dust, a hypothetical material that could interact with light in entirely new ways. Picture a substance that doesn't just absorb photons but transforms them, bending or scattering them at wavelengths our instruments can't easily trace. Some theories suggest these particles could be ultra-cold, barely interacting with ordinary matter, or even made of exotic compounds forged in the extreme conditions of the early universe. Others propose they're not dust at all, but a new class of quantum-scale objects lurking between the cracks of known physics. The search for this elusive material is pushing telescopes to their limits. Instruments like the James Webb Space Telescope are scanning distant galaxy clusters for subtle distortions in starlight that might betray the presence of unseen dust clouds. Meanwhile, lab experiments are attempting to recreate hypothetical dark dust particles under controlled conditions, hunting for any flicker of interaction that could explain their cosmic hiding places. Yet, even if dark dust exists, the mystery deepens. If these particles are so effective at hiding light, why haven't they left other traces in the cosmos? And how could they form on scales vast enough to dim billions of suns? The answers might lie in the universe's infancy, when conditions were so extreme that matter behaved in ways we're only beginning to understand. For now, intergalactic dust remains a tantalizing maybe, a shadowy veil that might conceal more than just light, but secrets about the fabric of reality itself. The universe isn't just expanding, it's stretching light itself into oblivion. Imagine a cosmic rubber band pulling photons from distant galaxies until their wavelengths grow longer, redder, and fainter. This phenomenon, called redshift, is why the light from faraway stars appears dimmer than it should. But here's the catch: while redshift can explain why some light fades, it doesn't account for the sheer scale of the missing glow. The numbers still don't add up. It's like trying to explain a disappearing lake by pointing out evaporation. Yes, some water is lost, but not enough to drain the entire basin. So why does redshift fall short? The answer lies in the speed of the universe's expansion. In the modern cosmos, galaxies drift apart at a steady pace, stretching light gradually. But in the universe's infancy, something extraordinary may have happened. A fleeting moment of hyper-accelerated expansion known as inflation. Picture a balloon inflating so rapidly that patches of its surface vanish from view before light can even reach them. If this occurred, it could have permanently severed entire regions of the cosmos from our observable universe, effectively erasing their light from existence. The implications are staggering. If inflation or another burst of rapid expansion scattered pockets of light beyond the cosmic horizon, it would mean we're not just missing photons. We're missing entire chapters of the universe's story, realms of space now receding faster than their light can ever reach us. This isn't just about dimmed starlight, it's about a fundamental limit to what we can see, a cosmic curtain drawn across parts of reality itself. Yet even this theory leaves gaps. If inflation erased light so thoroughly, why do we see any ancient light, like the afterglow of the Big Bang in the cosmic microwave background? Some researchers argue that inflation's effects might be patchy. Some light escaped, while other regions were stretched into darkness. Others propose that expansion isn't the only villain. Could something else, acting in tandem with redshift, be amplifying the light deficit? The hunt for answers is pushing cosmology to its limits. Telescopes now scour the sky for subtle patterns in the cosmic microwave background, hunting for echoes of primordial expansion. Meanwhile, physicists simulate the early universe in supercomputers, testing whether faster-than-light stretching could leave behind the voids we observe today. Every clue suggests the same unsettling truth. The universe might be hiding its light not just behind distance or dust, but in realms we can never access, locked away by the relentless expansion of space itself. What's truly humbling is the scale of the mystery. We're not just grappling with missing light, we're confronting the possibility that the universe is fundamentally unknowable in parts, its history fragmented by forces that outran light itself. And if that's the case, the darkness above us isn't empty. It's a mirror reflecting the limits of our vision and the audacity of our quest to understand it all. What if the missing light isn't lost at all, but simply slipped through a hidden doorway? String theory, one of the most radical ideas in modern physics, suggests our universe might be floating in a higher dimensional space, like a sheet of paper suspended in a vast, unseen room. If these extra dimensions exist, they could be acting as cosmic drains, quietly whisking away photons from our observable reality. Imagine holding a flashlight underwater. Some light escapes into the air above, invisible to anyone below the surface. Could our universe's missing glow be doing the same, vanishing into dimensions we can't perceive? The math behind this idea is both elegant and unsettling. In string theory, the fundamental particles of the universe aren't dots but tiny, vibrating strings. These strings can oscillate in ways that require more than the 3 spatial dimensions we experience daily. Some models suggest up to 10 or 11 dimensions might exist, curled up so tightly they're undetectable at human scales. But here's where it gets wild. If even one of these hidden dimensions were slightly unfurled, light could bleed across its boundary, carrying energy into realms beyond our reach. It's like radio static fading as you drive out of range, except in this case, the signal isn't fading. It's crossing into a reality where our antennas can't tune in. Critics argue this sounds like science fiction, and they're not entirely wrong. No direct evidence proves extra dimensions exist, let alone that they're stealing our light. But tantalizing clues linger. Particle colliders like the Large Hadron Collider have glimpsed anomalies in energy distributions during high-speed collisions, brief flickers where energy seems to vanish without a trace. Could these be moments when particles or the light they emit briefly dip into another dimension? Even more provocative are observations of gravity's behavior at microscopic scales. Some experiments suggest gravity weakens slightly at tiny distances, as if its force were leaking away. If gravity can do it, why not light? The implications would rewrite physics as we know it. If light can escape into other dimensions, our entire understanding of the universe's energy budget is incomplete. We might be living in a cosmic house with rooms we've never entered, where the glow of distant stars lingers just out of view. Future experiments could change everything. Next-generation colliders, like the proposed Future Circular Collider, might reach energies high enough to probe these hidden realms directly. Telescopes hunting for gravitational waves, ripples in spacetime itself, could stumble upon echoes of collisions in higher dimensions, like hearing voices through a wall. Yet the boldest idea isn't just about missing photons. If light crosses dimensions, what else might be slipping through? Could dark matter itself be ordinary matter from another dimension, casting a shadow into ours? The questions spiral outward, each more dizzying than the last. For now, extra dimensions remain a breathtaking what if, but in a universe where billions of suns worth of light have vanished without explanation, the most thrilling possibilities often lie just beyond the edge of the known. Picture trillions of miniature black holes, each no larger than an atom, drifting unseen through the cosmos like invisible piranhas. These aren't the colossal monsters we're used to. These are primordial black holes, hypothetical relics forged in the chaos of the Big Bang itself. Unlike their supermassive cousins, which form from collapsing stars, these tiny titans could have been born from the intense density fluctuations of the infant universe, condensed into gravitational traps so small they'd slip through matter like ghosts. And if they exist, they might be the universe's most efficient light thieves, silently absorbing photons across billions of years without leaving a trace. The math is compelling. If just a fraction of the early universe's energy crystallized into these microscopic black holes, their combined appetite could account for the missing light we've been chasing. Think of it like a swarm of cosmic dust mites, individually insignificant, but en masse capable of devouring the equivalent of 1 billion suns. Some models suggest they could even solve two mysteries at once: the missing light and the nature of dark matter. If primordial black holes make up even a portion of dark matter's invisible bulk, they'd be everywhere, floating between stars, weaving through galaxies, their collective gravity shaping the cosmos while their tiny event horizons snack on passing light. But how would we ever detect something so small and dark? Traditional telescopes can't spot objects that emit no light, but physicists have devised ingenious workarounds. One method involves watching for subtle flickers in distant stars. If a primordial black hole passes between us and a star, its gravity would bend the star's light like a lens, creating a brief brightening, a telltale blip in the data. Another approach studies the echoes of the Big Bang. If these black holes were numerous in the early universe, their evaporation, predicted by Stephen Hawking's theory, might have left faint thermal fingerprints in the cosmic microwave background, like ashes from a long-cooled fire. The most tantalizing clue might lie in gravitational waves. When two primordial black holes collide, they should send ripples through spacetime, shudders so faint our current detectors might miss them, but future observatories could catch. In 2017, the LIGO collaboration detected gravitational waves from merging black holes, some oddly lightweight for their cosmic era. Could these have been primordial survivors? The data isn't conclusive, but it's enough to keep scientists hunting. Yet the theory isn't without hurdles. If primordial black holes are so abundant, why haven't we seen more evidence of their lensing effects? And how did they avoid disrupting the delicate structures of early galaxies? Some researchers argue they'd have left scars in the cosmic web we'd have spotted by now. Others counter that their distribution could be patchy, clustered in cosmic voids where their shadows would blend into the darkness. What's thrilling is the sheer audacity of the idea. Tiny black holes born in the first seconds of existence, lurking unseen while sculpting the universe's light and mass. If proven, it would mean the cosmos is far stranger than we imagined, not just expanding, not just filled with dark matter, but infested with invisible quantum pits, each a silent witness to the universe's fiery birth. And if they're not out there, well, the hunt for the missing light just got even more interesting. We take it for granted that light lasts forever, that the glow from distant stars will always travel across the cosmos untouched by time. But what if that's not true? What if photons, the tiny packets of energy that make up light, aren't as stable as we think? Some physicists are daring to ask a startling question. Could light itself be fading away, slowly decaying into particles so elusive we can't even detect them? It sounds like something from a dystopian sci-fi novel, but this idea, photon decay, could rewrite our understanding of the universe's fate. The math behind this theory is as elegant as it is unsettling. If photons had even a tiny chance of breaking down over billions of years, the cumulative effect would be staggering. Imagine a cosmic hourglass, its sands trickling away grain by grain. Now replace those grains with photons and the hourglass with the entire observable universe. Over eons, entire galaxies would dim, their light dissolving into invisible remnants. The night sky, already missing billions of suns, would grow darker still, not because the stars died, but because their light simply evaporated. But why would photons decay at all? In our current model of physics, they're massless, stable, eternal. Yet some extensions of quantum theory suggest there might be ghostly particles even lighter than photons' actions or sterile neutrinos, perhaps, that photons could transform into under the right conditions. Picture a candle flame not blowing out but turning into a cold, dark mist. If this happens, it would be so subtle we'd never notice it in a lab. Only across cosmic distances and timescales would the effect become visible, like spotting a single missing pixel in a screen the size of the universe. The challenge is proving it. Photon decay would be achingly slow, so slow that even over billions of years, only a handful of photons in a galaxy's worth of light might vanish. But here's the catch. When you scale that up to the entire cosmos, those handfuls add up to the missing light we've been searching for. Scientists are scouring ancient light sources, quasars, gamma-ray bursts, the cosmic microwave background, for any hint that photons lose energy or vanish disproportionately over time. So far, the evidence is frustratingly silent, yet the silence itself is telling. If photons were decaying, we'd expect to see certain wavelengths dimming faster than others, like colors fading unevenly on an old painting. The fact that we haven't spotted this pattern doesn't rule out decay entirely. It just means the process, if it exists, is even stranger than we imagined. Some theorists propose that photon decay might require conditions we can't replicate, like interactions with hidden quantum fields or collisions with undiscovered particles. Others suggest it could be a relic of the early universe, a phantom effect lingering from when the laws of physics were fundamentally different. What makes this idea so haunting isn't just the science, it's the existential weight. If light isn't eternal, then neither is our window into the cosmos. Every star we see, every galaxy we study, might one day wink out not because they've died, but because their light has quietly unraveled into nothingness. It's a reminder that the universe's greatest mysteries aren't always about what's out there sometimes. They're about what's slipping through our fingers, one photon at a time. Galaxies aren't just islands of stars, they're cosmic engines, churning out winds so powerful they can blow entire oceans of light into the void. When a massive star explodes as a supernova, it doesn't just vanish in a flash. It unleashes a shockwave of energy, hurling gas and dust outward at millions of miles per hour. Multiply that by thousands of exploding stars, and you've got a galactic hurricane capable of sweeping light-emitting material clear out of its home galaxy and into the darkness between worlds. This isn't just theoretical. Telescopes have caught galaxies red-handed, their luminous gas tails stretching for thousands of light years like cosmic comet trails. In some extreme cases, up to 90% of a galaxy's visible light is being stripped away by these winds, carried off into intergalactic space where it diffuses into near invisibility. Imagine a candle flame caught in a gale. The light doesn't vanish, but it's scattered so thin it becomes impossible to see from a distance. That's the fate of countless photons, banished by forces as relentless as they are invisible. But here's the catch: while galactic winds are undeniably fierce, they can't account for all the missing light. The numbers still don't add up. Even if every galaxy in the universe were hemorrhaging light this way, the total deficit would only explain a fraction of the glow we're searching for. It's like realizing a burst pipe can't possibly drain an entire reservoir. There must be other leaks, other forces at work. One clue lies in the wind's aftermath. As these gusts of gas and light pour into intergalactic space, they don't just disappear. They collide, mix, and form vast, diffuse clouds that glow faintly in ultraviolet, a wavelength many telescopes struggle to detect. Could this lost light be hiding in plain sight, camouflaged by its own scattering? Some astronomers think so, pointing to recent observations of these dim, sprawling halos around distant galaxies. But even these ghostly glows fall short of balancing the cosmic ledger. The puzzle deepens when we consider quasars, the universe's most luminous objects. These supermassive black holes, feasting on gas at the centers of galaxies, blast out winds so intense they can clear entire regions of space. Yet studies show that while quasars can dim their host galaxies, their collective impact still doesn't cover the missing light's staggering scale. It's as if we've found a few broken faucets, but the bulk of the water is still unaccounted for. What's fascinating is how these winds might team up with other cosmic phenomena. Could they be funneling light toward regions where dark matter or primordial black holes lie in wait? Or might they interact with intergalactic dust in ways we haven't yet imagined? Every answer seems to lead to new questions, each more tantalizing than the last. For now, galactic winds remain a key piece of the puzzle, not the full solution, but a reminder of how dynamic and violent the universe truly is. Light doesn't just fade or vanish, it's chased, scattered, and reshaped by forces we're only beginning to understand. And somewhere in that chaos, between the gusts and the shadows, the secret of the missing billion suns might still be waiting to be found. At the tiniest scales imaginable, far smaller than an atom, even smaller than a proton, space itself might not be the smooth, unbroken fabric we picture. Instead, it could be a seething, bubbling froth known as quantum foam, where particles and forces flicker in and out of existence in a chaotic dance. This isn't just poetic metaphor, it's a prediction from the marriage of quantum mechanics and general relativity, suggesting that space-time itself has a granular, unpredictable texture if you zoom in close enough. And if that's true, it might hold the key to the missing light mystery. Think of it like trying to shine a flashlight through a dense fog. Normally, light travels in straight lines, but in a turbulent medium, it scatters, bending and diffusing until the beam weakens or even vanishes from view. Quantum foam could act like that fog, an invisible, churning sea of microscopic twists and folds in space-time, subtly disrupting photons as they journey across the cosmos. Over billions of light-years, even the tiniest scattering could add up, leaving entire stretches of the universe dimmer than they should be, the wildest part. This isn't just about light getting lost. Some theories suggest quantum foam might actually absorb photons, swallowing them into the foam's fleeting voids. Picture a sponge dunked in water, except instead of water, it's soaking up starlight, trapping it in quantum-scale pockets we can't observe. If true, this would mean the universe's missing light isn't just scattered or transformed. It's been erased at the most fundamental level, dissolved into the froth of spacetime itself. Testing this idea isn't easy. Quantum foam's fluctuations are unimaginably brief and small, far beyond the reach of current instruments, but scientists aren't giving up. One approach involves ultra-precise laser experiments, where researchers fire photons across vast distances and look for subtle changes in their arrival times. If spacetime is foamy, photons of different energies should stumble slightly differently through the quantum turbulence, like runners tripping over an uneven track. Another method studies high-energy gamma rays from distant cosmic explosions. If quantum foam exists, these rays should show telltale signs of scattering, like a flashlight beam flickering after passing through a storm. So far, the evidence is inconclusive. Some observations hint at anomalies that could align with quantum foam, while others contradict it outright. But the mere possibility reshapes how we see the cosmos. If spacetime's tiniest structures are stealing light, it would mean the universe's grandest mystery, the vanishing of a billion suns, is rooted in the quantum realm's shadowy chaos. What's thrilling is the scale of the implication. Quantum foam isn't just a curiosity for physicists. It could be a hidden actor in the cosmic drama, quietly shaping what we see and what we don't across billions of years. And if future experiments confirm its role, we'll have uncovered something even more astonishing, that the fabric of reality itself is woven with threads so strange they can make light disappear. Hidden galaxies so faint they blur into the blackness of space itself might be the universe's best-kept secret. We're used to picturing galaxies as blazing whirlpools of stars, their spirals glowing against the cosmic dark. But what if some galaxies are more like cobwebs, their light stretched so thin it's nearly invisible? That's the enigma of ultra-diffuse galaxies, a bizarre class of cosmic objects that defy everything we thought we knew about how galaxies form. These ghostly structures can span the same width as the Milky Way but contain just 1% of its stars, their sparse collections of suns floating in vast halos of dark matter. If these shadowy giants are more common than we realized, they could be silently soaking up starlight, hiding it in plain sight. The discovery of ultra-diffuse galaxies was almost accidental. In 2015, astronomers using the Dragonfly telephoto array, a telescope designed to spot extremely dim objects, stumbled upon galaxies so faint they'd been overlooked for decades. Unlike typical galaxies, which blaze with the collective glow of billions of stars, these were more like cosmic mirages, their light diluted across such enormous volumes that they blended into the background. Some were so transparent you could see right through them, their few stars spaced so far apart that night on a planet inside one would be pitch black, the nearest star barely a speck in the sky. What makes these galaxies so puzzling isn't just their dimness, it's what's holding them together. With so few stars, their gravity shouldn't be enough to prevent them from flying apart. Yet they endure, suggesting something invisible, likely vast reservoirs of dark matter, is acting as cosmic glue. This raises a tantalizing possibility. Could there be countless more of these faint giants, their dark matter halos trapping light in ways we've never noticed? If so, they might form a hidden scaffold throughout the universe, a network of dim galaxies collectively absorbing or scattering light on scales we've yet to measure. The hunt for these ghostly galaxies is accelerating. Next-generation telescopes like the Vera-C, Rubin Observatory with its unprecedented wide-field view are scanning the skies for more ultra-diffuse candidates. Meanwhile, radio astronomers are probing their dark matter content by studying how these galaxies bend passing light, searching for clues about how much mass and how much missing light they might contain. Early estimates suggest that if ultra-diffuse galaxies are as plentiful as some theories predict, they could account for a significant fraction of the universe's light deficit. But there's a twist. Not all ultra-diffuse galaxies are created equal. Some appear to be failed galaxies that never formed many stars, while others might be the remnants of violent collisions, their stars scattered like dust in a cosmic wind. A few even seem to be entirely devoid of dark matter, challenging our understanding of how such fragile structures survive. This diversity complicates the picture. If these galaxies vary wildly in composition, their role in the missing light mystery might be subtler than we hoped. The implications stretch beyond astronomy. If ultra-diffuse galaxies are hiding light, they're also hiding history. Their faint stars might preserve pristine chemical signatures from the early universe, untouched by the violent processes that shaped brighter galaxies. They could be cosmic time capsules, offering glimpses into an era when the first galaxies were just beginning to flicker to life. And if their dark matter content is as vast as suspected, they might rewrite the rules of how matter clumps together in the cosmos. What's clear is the universe is far more inventive than we imagined. It doesn't just build galaxies of fire and light. It crafts them from whispers and shadows, from dark matter and stray stars. And if we've missed entire populations of these faint giants, the missing light might not be lost at all. It might simply be waiting quiet, diffuse, and patient for us to learn how to see it. Light doesn't just travel, it lingers, carrying snapshots of the universe's past across unimaginable distances. When we peer at a galaxy a billion light-years away, we're not seeing it as it is today, but as it was a billion years ago, its light frozen in time like a message in a bottle. This cosmic delay means the universe we observe is a patchwork of eras, a collage where some regions appear young while others seem ancient. But here's the catch. If light takes so long to reach us, could there be entire galaxies whose light hasn't arrived yet? Vast stretches of the cosmos might still be hidden, their photons crawling toward us at the speed of light, trapped in a sort of interstellar purgatory. This idea, called the look-back time effect, explains why parts of the universe appear dark to us, but it doesn't fully solve the mystery of the missing light. After all, if all the light is simply delayed, the total energy in the universe should still balance out over time. Yet the deficit persists, suggesting something else is at play. Still, the concept reshapes how we think about the cosmos. Imagine standing in a pitch-black forest at night, hearing distant voices but seeing no one. You know people are out there speaking, moving, but their light, their presence hasn't reached you yet. That's our relationship with the universe. We're surrounded by voices, stars, galaxies, cosmic events whose signals are still en route, lost in the vastness of space and time. The implications ripple outward. If some light is delayed, our entire understanding of cosmic history might be skewed. Surveys of the early universe could be missing entire populations of galaxies whose light is still traveling, making the young cosmos appear emptier than it truly was. Telescopes like the James Webb Space Telescope are designed to detect the faintest, oldest light, pushing our vision closer to the Big Bang. But even Webb has limits. It can't see what hasn't arrived. Some theorists speculate that the universe's dark age, that shadowy period before the first stars ignited, might not have been as dark as we think. What if galaxies were already shining, but their light is still streaming toward us, trapped in the past? The real twist comes when we consider the universe's accelerating expansion. As space stretches faster, distant light struggles to keep up, its wavelengths stretched into obscurity. Some photons may never reach us at all, their journey eternally outpaced by the expansion of space itself. This isn't just about delay, it's about light being erased from our future observations, a cosmic foreclosure on what we're able to see. The most distant galaxies we detect today might one day vanish from our view entirely, their light redshifted into nothingness, their stories forever untold. So where does that leave the missing light? Time delays alone can't explain the deficit, but they force us to confront a humbling truth. The universe we see is just a sliver of what's out there. We're not just missing light, we're missing context, history, maybe even entire chapters of cosmic evolution. Every telescope image, every dataset, is a fragment of a much larger story, one we're piecing together in real time as photons trickle in from the void. The darkness above us isn't empty. It's a theater with the lights still down, the show about to begin, and we're front-row witnesses waiting for the curtains to rise. What if gravity, the force that holds planets in orbit and binds galaxies together, doesn't work the way we think it does? For over a century, Einstein's theory of general relativity has been the gold standard for understanding gravity, describing it as the curvature of spacetime by mass. But what if that picture is incomplete? A daring group of physicists proposes an alternative, modified Newtonian dynamics, or MUND. This theory suggests that gravity behaves differently on the vast scales of galaxies and galaxy clusters, subtly altering how light moves through the cosmos. If correct, it could rewrite the rules of astrophysics and finally account for the universe's missing light. Here's the radical idea at MUND core. Instead of invoking dark matter to explain why galaxies rotate faster than predicted, MUND tweaks the equations of gravity itself. Imagine driving a car where the steering wheel becomes more sensitive the farther you turn it. In MUND universe, gravity strengthens slightly at extremely low accelerations, the kind found in the outskirts of galaxies. This tiny adjustment could explain why stars on the fringes of galaxies orbit faster than expected without needing invisible matter to tug on them. But here's where it gets wild. If gravity truly works this way, it wouldn't just affect stars. It would also bend light differently, potentially redirecting or dispersing photons in ways that make them vanish from our observations. The implications are staggering. If MUND is right, the missing light might not be absorbed or transformed. It could simply be following paths we've miscalculated. Picture a maze of funhouse mirrors, where light ricochets in unexpected directions, leaving some areas brighter and others eerily dark. On cosmic scales, this could mean entire swaths of starlight are being deflected into cosmic voids or stretched into wavelengths we can't detect. Telescopes might be staring right at the missing photons without realizing it, their instruments tuned to the wrong assumptions about gravity's grip. Yet MUND remains fiercely controversial. Critics point to bulletproof evidence for dark matter, like the way galaxy clusters bend light in ways MUND struggles to explain. Others argue that tweaking gravity is a slippery slope. Once you alter one law, how many others must follow? But the theory's defenders counter with puzzles of their own. Why do some galaxies seem to lack dark matter entirely? Why do certain star systems behave as if gravity strengthens precisely where MUND predicts? These anomalies keep the debate alive, fueling experiments that could tip the scales. The most tantalizing clue might lie in the cosmic microwave background, the afterglow of the Big Bang. If an inversion of gravity shaped the early universe, it should have left subtle fingerprints in this ancient light. So far, the data favors dark matter, but the margins are slim and future telescopes could reveal surprises. Meanwhile, lab experiments are testing whether gravity behaves differently at ultra-low accelerations, probing the theory's predictions on tabletop scales. What's thrilling isn't just the science, it's the audacity to question Einstein himself. For decades, his theory has withstood every test, bending but never breaking. Yet science thrives on challenges and forces us to ask, what if we've been missing something fundamental? Even if the theory falls short, the questions it raises could lead us to deeper truths about gravity, light, and the hidden structure of the cosmos. After all, the greatest discoveries often begin with two simple words. What if cosmic strings sound like something straight out of science fiction? Thin, unimaginably dense threads stretching across the universe, thinner than an atom yet heavier than entire galaxies. These theoretical relics born in the chaos of the Big Bang aren't just cosmic oddities. They could be invisible snares, bending or even trapping light in ways that leave entire regions of the cosmos unnaturally dark. Picture a spiderweb strung between trees, catching dewdrops in the morning sun. Now imagine that web is made of spacetime itself, and those dewdrops are photons, particles of light snagged mid-flight, their glow dimmed or redirected into the void. The math behind cosmic strings is as elegant as it is mind-bending. In the first moments after the Big Bang, the universe underwent a series of phase transitions, like water freezing into ice. But if these transitions weren't perfectly smooth, tiny cracks might have formed in the fabric of reality. Cosmic strings. These defects wouldn't just sit there. They'd vibrate, snap, and even loop back on themselves, creating gravitational disturbances that ripple outward. And here's where light comes in. A passing cosmic string could act like a gravitational lens, bending light around it so severely that some photons get diverted entirely, leaving behind patches of unexpected darkness. What makes this idea so compelling is its sheer audacity. Unlike black holes or dark matter, cosmic strings wouldn't just absorb or scatter light, they'd warp the very stage it travels on. Think of it like a wrinkle in a projector screen, distorting the image in ways no one expected. Some models suggest these strings could even create shadow zones, regions where light appears to vanish because it's been bent into paths our telescopes can't trace. Over billions of years, the cumulative effect could account for the missing glow we've been chasing. But how do you hunt for something so elusive? Cosmic strings, if they exist, would be nearly invisible. They don't emit light, and their gravitational signatures would be subtle. Yet scientists have devised ingenious ways to search for them. One method involves scanning the cosmic microwave background, the afterglow of the Big Bang, for telltale kinks or tears that a passing string might have left behind. Another looks for double images of distant galaxies, a sign that their light has been split by a string's gravity, like a prism splitting sunlight. So far, no smoking gun has been found, but the search has turned up tantalizing anomalies, odd patterns in galaxy distributions, unexplained gaps in the cosmic web that keep theorists intrigued. The wildest possibility, cosmic strings might not just hide light, they could be hiding entire structures. If strings are as massive as some theories suggest, their gravity could pull matter into filaments, creating shadowy superhighways of galaxies we've yet to map. It's a humbling thought that the universe's missing light might be tied to structures so vast and strange, we're only beginning to guess at their existence. For now, cosmic strings remain a beautiful what-if, a reminder that the cosmos is far stranger than our best theories can capture. But in a mystery as deep as the missing light of a billion suns, even the most outlandish ideas deserve a seat at the table. After all, the universe has never been shy about surprising us. Why start now? Neutrinos are the universe's ultimate ghosts, particles so elusive they pass through entire planets like they're not even there. Billions stream through your body every second, leaving no trace. These nearly massless phantoms rarely interact with matter, making them almost impossible to detect. But what if these cosmic ghosts are doing more than just passing through? What if they're quietly stealing light itself? The idea sounds like science fiction, but the math is startlingly plausible. Neutrinos are produced in staggering quantities by the sun, by supernovas, even by the Big Bang's fading echo. They outnumber atoms in the universe by 1 billion to 1. And while each neutrino barely notices matter, their sheer abundance means even the tiniest chance of interacting with light could add up over cosmic distances. Picture a vast, invisible net cast across the universe. Its threads so fine they only catch the rarest photons, but with enough threads, the catch becomes significant. How could a neutrino intercept light? Most models assume neutrinos and photons ignore each other, but some theories suggest that under extreme conditions, like those in the early universe, they might have exchanged energy or even transformed into one another. If that interaction left a lingering effect, neutrinos could still be siphoning off photons today, like stealthy thieves plucking coins from a fountain. The stolen light wouldn't vanish entirely. It might shift into wavelengths we can't detect or scatter into the cosmic background, blending into the noise. Proving this would require experiments of almost absurd sensitivity. Imagine trying to hear a whisper in a hurricane. That's the challenge of spotting neutrino-photon interactions. Yet scientists are trying deep underground detectors like IceCube and Super Camiok, and watch for rare neutrino collisions, hoping to catch a flicker of unexpected behavior. Other teams analyze the cosmic microwave background for anomalies that could hint at lost light. Even particle colliders are in on the hunt, smashing particles together to recreate conditions where neutrinos and photons might briefly tango. The implications would rewrite physics. If neutrinos are stealing light, it would mean these ghostly particles are far more complex than we thought, not just passive bystanders but active players in shaping the cosmos. It could also solve another mystery: why neutrinos have mass at all. Their tiny weights were never predicted by the standard model of particle physics, and this could be the missing link explaining why. Yet the theory isn't without skeptics. If neutrinos interact with light, why haven't we seen evidence in existing data? Some argue the effect would be too small to matter, like a single raindrop trying to empty a lake. Others counter that we've only scratched the surface, that the real action happens in realms of energy or density we haven't probed yet. What's thrilling is the sheer scale of the question. We're not just talking about particles playing hide and seek. We're talking about a potential secret handshake between light and one of the universe's most enigmatic particles, a handshake that might have dimmed the cosmos itself. And if the answer's yes, well, it would mean the universe's greatest magic trick wasn't performed by black holes or dark matter, but by ghosts. Plasma isn't just the stuff of lightning bolts or neon signs. It's the universe's most common state of matter, a sea of electrically charged particles so vast it fills the spaces between galaxies. This ionized gas doesn't just sit there, it dances, twisting and warping under the influence of magnetic fields and cosmic winds. And here's where things get interesting. Plasma doesn't just let light pass through untouched. It can absorb photons, shuffle their energy, and spit them back out in entirely new forms. Think of it like a cosmic game of telephone, where the original message, the light we expect to see, gets garbled along the way, emerging as something unrecognizable. The key lies in plasma's ability to shift light into wavelengths our telescopes can't catch. Imagine tuning a radio to a static-filled frequency, just barely hearing whispers of a song beneath the noise. That's what might be happening on a galactic scale. Ultraviolet light, for instance, can get absorbed by plasma and re-emitted as low-energy infrared, a wavelength so faint it blends into the background glow of the universe. Over vast distances, this process could effectively erase starlight from our observations, not by destroying it, but by disguising it. Some astronomers call this dimming by transformation, and it's one of the sneakiest ways the cosmos might be hiding its light. But plasma's tricks don't stop there. In regions where magnetic fields are strong, like around black holes or in the wakes of colliding galaxies, plasma can act like a funhouse mirror, bending light into chaotic paths. Photons that should be streaming toward us get tangled in these magnetic knots, diverted into cosmic dead ends. It's as if the universe has built in blind spots, places where the rules of optics get rewritten by the whims of superheated gas. The strangest part, we might already be seeing hints of this. Observations of distant quasars show patches where light flickers unpredictably, as if something invisible, like a turbulent plasma cloud, is scattering the beams before they reach us. The challenge is untangling the mess. Plasma's behavior is notoriously hard to model, especially at cosmic scales. Supercomputer simulations try to replicate how ionized gas interacts with light, but even the best algorithms struggle to account for every twist and ripple. Some theories suggest that pockets of dark plasma, regions so diffuse or magnetically scrambled they don't emit detectable signals, could be lurking throughout the cosmos. If these exist, they'd be the perfect hideouts for missing photons, their energy dissipated into the void without a trace. Yet there's hope on the horizon. New telescopes like the upcoming Square Kilometre Array are designed to peer through plasma's veil, mapping its influence with unprecedented precision. Others, like the James Webb Space Telescope, are spotting the infrared echoes of transformed light, piecing together where the missing energy might have gone. Every flicker, every anomaly in the data brings us closer to solving the puzzle, not by finding the light we lost, but by learning to see the universe in wavelengths we once ignored. What's fascinating isn't just the science, it's the irony. Plasma, the very substance that makes stars shine, might also be the reason their light seems to vanish. It's a reminder that the cosmos doesn't play by simple rules. Sometimes the answers aren't in what's missing, but in what we've yet to learn how to detect. The darkness above us isn't empty. It's a mirror reflecting back the limits of our vision and the boundless creativity of the universe itself. Dark energy isn't just stretching the universe, it might be dissolving its light. We've known for decades that this mysterious force is accelerating the expansion of space, pushing galaxies apart faster and faster. But what if its influence doesn't stop there? Some physicists suspect dark energy could be interacting with photons in ways we've never imagined, subtly draining their energy over cosmic timescales. Picture a candle not just burning down, but having its flames siphoned away by an invisible hand. If true, this wouldn't just explain missing starlight. It would mean the universe is engaged in a slow-motion vanishing act, erasing its own glow from within. The math behind this idea is as elegant as it is unsettling. In a universe dominated by dark energy, empty space isn't truly empty. It's a seething quantum field brimming with potential. Photons traveling through this froth might lose tiny amounts of energy with every passing light year, like hikers shedding stamina on an endless uphill climb. Normally, this loss would be negligible, but stretch it across billions of years and billions of light years, and those drips add up to an ocean. The result: distant starlight could arrive dimmer than expected, not because it was absorbed or scattered, but because dark energy itself sapped its strength along the journey. Here's where it gets eerie. If dark energy strips photons of energy, it wouldn't just dim the cosmos, it would fundamentally alter its fate. Right now, we assume the universe will end in a heat death, where expansion spreads matter so thin that stars can no longer form, leaving space cold and dark. But if dark energy actively degrades light, that future could arrive far sooner. Galaxies wouldn't just fade from view as they race away. Their light might dissolve before it even reaches the void, like messages written in vanishing ink. The night sky, already missing billions of suns, could grow darker at an accelerating pace, not from distance but from something far stranger, a force that doesn't just expand space but consumes its stories. Critics argue there's a glaring flaw in this theory. We've never detected dark energy interacting with anything, let alone light. It's famously aloof, influencing the cosmos only through its push against gravity. But proponents counter that absence of evidence isn't evidence of absence. After all, dark energy itself was only discovered 25 years ago when astronomers noticed the universe's expansion wasn't slowing down as expected. Could we be on the brink of another revelation, one that shows dark energy's reach extends beyond geometry into the very fabric of light? Experiments are already hunting for clues. Telescopes like the Dark Energy Survey scrutinize distant supernovae for signs that their light dims in ways that can't be explained by redshift alone. Others study the cosmic microwave background for anomalies that might betray dark energy's fingerprints. Even particle accelerators are in on the act, attempting to recreate phantom interactions between photons and hypothetical dark energy particles in controlled settings. So far, the results are inconclusive, but in a mystery this profound, even null results are progress, narrowing the possibilities one by one. What's at stake isn't just a missing light puzzle, it's our understanding of reality's rulebook. If dark energy can meddle with photons, it would mean the universe operates by laws far more interconnected than we dreamed. Energy wouldn't just be conserved, it could be traded, borrowed, or even lost to the void. And that changes everything. The darkness above us might not be passive emptiness, but something far more dynamic, a canvas where light and shadow wage a silent war, with dark energy quietly tilting the scales. The most humbling thought, we might be witnessing only the opening act. If dark energy's influence grows as the universe expands, its light-draining effect could one day dominate, leaving future civilizations, if any exist, to gaze up at a sky not just starless but stripped of light's very memory. It's a reminder that the cosmos doesn't just hide its secrets in space but in time, and the deeper we look, the more we realize how much we've yet to see. Quantum entanglement is one of the most baffling phenomena in physics, a cosmic magic trick where two particles become linked so deeply that changing one instantly affects the other, no matter how far apart they are. Einstein famously called it spooky action at a distance, and for good reason. It defies our everyday intuition about how the universe should work. But here's where it gets even stranger. What if this spooky connection isn't just a laboratory curiosity? What if it's happening on a galactic scale, with entangled photons vanishing from our observations because their fates are tied to particles we can't see? Imagine tossing a pair of dice that always land on matching numbers, even if you roll them in different cities. Now replace those dice with photons, particles of light, and the cities with opposite ends of the universe. That's the essence of quantum entanglement. When photons are entangled, measuring one immediately determines the state of its partner, no matter how far apart they've traveled. Now consider this: if entangled photons are being created in distant cosmic events, supernovas, black hole collisions, even the Big Bang's afterglow, could some of them be disappearing because their entangled counterparts have been absorbed, scattered, or redirected into states our telescopes can't detect? It's as if the universe is playing a shell game with light, hiding photons not by destroying them, but by locking them into pairs where only one half remains visible. This idea is still speculative, but the math is tantalizing. If even a fraction of the universe's light is entangled, it could create a vast, invisible network of correlated photons, a hidden tapestry of energy woven into the fabric of space itself. Some theories suggest that entangled photons might not just vanish from view. They could be shifting into wavelengths or quantum states that slip past our instruments entirely. Picture a radio tuned to the wrong frequency, missing entire stations broadcasting just outside its range. Our telescopes might be facing a similar blind spot, oblivious to light that's technically still there, just encoded in a language we don't yet understand. The challenge, of course, is proving it. Quantum entanglement is notoriously fragile. Any interaction with the environment can break the spell, a process called decoherence. In the chaos of the cosmos, where light passes through magnetic fields, dust clouds, and gravitational warps, maintaining entanglement across billions of light-years seems nearly impossible. Yet some researchers argue that under the right conditions, like the ultra-smooth voids between galaxies, entangled photons could survive long enough to skew our observations. Others propose that entanglement might not need to persist. Even if the link breaks, the initial correlation could still scatter light in ways that leave gaps in our cosmic senses. Experiments are already pushing the boundaries. Quantum satellites like China's Missions have successfully entangled photons over distances of thousands of kilometers, proving that the effect can withstand the rigors of space. Future missions could test whether entanglement leaves detectable fingerprints in starlight, like subtle statistical anomalies in the way photons arrive from distant quasars. Meanwhile, lab experiments are simulating cosmic conditions to see how entanglement interacts with interstellar plasma, magnetic fields, and even the quantum foam of spacetime itself. Every test brings us closer to answering the ultimate question: is the universe's missing light hiding in plain sight, woven into a quantum code we're only beginning to crack? The implications stretch far beyond astronomy. If entanglement is shaping what we see and don't see in the cosmos, it would mean the universe is far more interconnected than we ever imagined. Light wouldn't just be a messenger from distant stars. It could be part of a vast, invisible dialogue, with photons whispering secrets to one another across the void. And if that's true, the darkness above us isn't empty. It's a mirror reflecting back the limits of our perception and the breathtaking possibility that the answers we seek are already here, entangled in the light we've yet to learn how to read. The cosmic microwave background isn't just a faint glow. It's the oldest light in the universe, a snapshot frozen in time from when the cosmos was just 380,000 years old. This afterglow of the Big Bang blankets the entire sky, a whisper of heat left over from a time when space itself was a seething plasma of particles and energy. But hidden within this ancient light might be the fingerprints of a cosmic crime scene, evidence of where and how a staggering amount of the universe's early brightness simply vanished. When we map the CMB, we're not just looking at a baby picture of the cosmos. We're staring at a puzzle. Tiny fluctuations in temperature, hotspots, and cold spots no larger than a fraction of a degree tell the story of how matter and energy were distributed in those first moments. But some of these patterns don't quite match our predictions. There are patches where the light seems oddly dim, as if something had drained energy from certain regions before the photons could begin their 13.8 billion-year journey to our telescopes. It's like finding faded sections in an otherwise vibrant painting, hinting at a brushstroke we didn't expect. One clue lies in the CMB's polarization, the way its light waves vibrate in specific directions. Certain patterns in this polarization, called B modes, could be the scars of primordial gravitational waves, ripples in spacetime from the universe's violent infancy. But here's the twist. Some theorists suggest these waves might also carry echoes of a cataclysmic event that erased light on a colossal scale. Picture a tsunami sweeping through the early cosmos, its gravitational force so powerful it scattered or absorbed photons before they could join the CMB's glow. If true, these waves wouldn't just be relics of the Big Bang, they'd be witnesses to a cosmic vanishing act. Then there's the cold spot, a mysterious region in the CMB that's significantly cooler than its surroundings. Some explanations propose it's a shadow cast by a supervoid, a vast, nearly empty region of space, but others wonder if it's something far stranger, a bruise left behind when a chunk of the universe's light was siphoned away. Imagine pouring water into a bowl, only to find one corner inexplicably dry. That's the level of anomaly we're dealing with, a deficit so stark it defies easy explanation. The most tantalizing possibility, the CMB might contain the ghosts of particles we've never detected. If certain hypothetical particles like sterile neutrinos or actions existed in the early universe, they could have absorbed or scattered photons in ways that left subtle gaps in the CMB's tapestry. These particles wouldn't just be hiding in the shadows, they'd be woven into the fabric of the cosmos itself, their presence etched into the light we're only now learning to decode. What makes this search so thrilling is its scope. The CMB isn't just a relic, it's a mirror, reflecting back the universe's deepest secrets. Every anomaly, every deviation from expectation, could be a clue pointing toward the missing light we've been chasing. And with next-generation telescopes like the Simons Observatory and Lightbird set to map the CMB in unprecedented detail, we might soon have the tools to read between the lines of this ancient text, uncovering stories written in photons long thought lost. The darkness we see today might not be empty at all. It could be filled with echoes, whispers of light that slipped through our fingers, waiting for us to piece together their story. And if we listen closely, they might just tell us where the universe hid its glow. What if the missing light isn't a cosmic mystery, but a clue that our universe isn't real? The simulation hypothesis, once relegated to science fiction, has gained startling traction among physicists and philosophers. The premise is unsettling. If an advanced civilization could create hyper-realistic simulations of entire universes, the odds that we're living in base reality plummet. And here's where the missing light comes in. Could this glaring gap in our observations be evidence of corners cut by the universe's programmers? A cosmic shortcut to save processing power, like a video game lowering render distance to handle vast open worlds. Think of it like this: every simulation has limits. Even the most powerful computer would struggle to perfectly calculate every photon in a universe as vast as ours. So what gets prioritized? The light we can easily see, stars, galaxies, the cosmic microwave background. But the faintest photons, the ones that should statistically exist in the farthest reaches. Maybe those get approximated or dropped entirely to conserve resources. It's not so different from how your phone dims background apps to keep the foreground running smoothly. The universe, in this view, might be doing the same, focusing its computational firepower on what's immediately observable while letting the distant, subtle details fade into the void. This isn't just wild speculation. certain anomalies in quantum physics already hint at something bizarre underlying reality. Take the double-slit experiment, where particles behave differently when observed, as if the universe is optimizing processing by only rendering precise details when necessary. The missing light could be another such artifact, a telltale sign that somewhere beyond our perception, an intelligence is making trade-offs to keep the simulation running. Even the speed of light itself might be a built-in limit, not a fundamental law, but a clock speed preventing the system from overloading. Critics, of course, dismiss this as unfalsifiable fantasy. After all, how do you prove you're inside a simulation when all your tools are part of that simulation? But proponents counter with eerie precision. The universe operates on mathematical laws so finely tuned that altering any constant by a fraction would make life impossible. That level of perfection, some argue, smells more like engineered design than random chance. And if the architects are out there, they've left breadcrumbs, not just in the missing light, but in the quantum weirdness that defies classical logic. Here's the twist: even if the simulation hypothesis is wrong, grappling with it reshapes how we approach cosmic mysteries. It forces us to ask whether the rules we take for granted, like light's behavior, might have deeper, stranger explanations. Maybe the missing photons aren't lost, but hidden in layers of reality we can't perceive, like pixels masked behind a video game's fog of war. Or perhaps the deficit reveals a flaw in our own assumptions, a blind spot in how we model the universe's energy budget. The simulation idea, for all its controversy, does something remarkable. It turns the missing light from a puzzle into a portal one that could lead to revelations far beyond astrophysics. Whether glitch or gap, the darkness above us might be more than empty space. It could be a question written in the negative: what don't we see and why? And the answer, whatever it is, might rewrite not just our maps of the cosmos, but our understanding of existence itself. The hunt for the universe's missing light is about to enter its most thrilling chapter, armed with telescopes so powerful they'll redefine what we think is possible. The James Webb Space Telescope, already revolutionizing astronomy, is just the beginning. Its infrared eyes pierce through cosmic dust, capturing whispers of light from the universe's first galaxies, light that might hold clues to where the rest vanished. But Webb isn't working alone. The Vera Rubin Observatory, poised to begin its 10-year legacy survey of space and time, will scan the entire southern sky every few nights, spotting changes so subtle they'd escape lesser instruments. Together, these observatories don't just expand our vision, they transform it, turning the cosmos into a crime scene where every faint glow or unexplained shadow could crack the case. What makes this new era so groundbreaking isn't just sharper images, it's the ability to see the invisible. Webb's infrared capabilities reveal heat signatures from objects too cold or dust shrouded to emit visible light, while Rubin's wide-field camera detects ultra-faint galaxies that previous surveys missed. Imagine combing a dark beach with a flashlight versus a floodlight suddenly. Treasures hidden for decades sparkle into view. Some theorists believe these tools might uncover vast populations of stealth galaxies, their stars so spread out they've evaded detection, or catch the infrared echoes of light absorbed and re-emitted by cold dust clouds. Others speculate we'll find entirely new classes of objects, perhaps dark matter halos glowing with feeble radiation, or primordial black holes betraying their presence through subtle lensing effects. But the real revolution lies in the unexpected. Every leap in observational power has revealed cosmic surprises: black holes, dark energy, galaxies where none should exist. This time, we might stumble upon structures or phenomena that don't just explain the missing light, but rewrite the rules of astrophysics. Consider the possibility of dark galaxies, not just dim, but completely devoid of stars, their immense gravity betraying them only through distortions in background light. Or imagine Webb spotting ghostly filaments of ionized gas, threading between galaxies like cosmic wiring, siphoning light into channels we never thought to trace. The data deluge will be unprecedented. Rubin alone will generate 20 terabytes nightly, enough to fill a library each week. Sifting through this avalanche requires AI trained to spot anomalies human eyes might dismiss, a flicker where none should be, a statistical blip in starlight distribution, a pattern of shadows aligning in ways that hint at hidden mass. It's detective work on a universal scale where the tiniest clue could unravel the mystery or deepen it. After all, the universe has a habit of answering our questions with riddles twice as perplexing. What keeps astronomers awake isn't just the hope of solving the puzzle, it's the thrilling uncertainty of what else we'll find. Every time we've built a better telescope, the cosmos has shown us how much we've underestimated its ingenuity. The missing light might be the thread that leads us to discoveries we can't yet name, new forces, unseen dimensions, or physics beyond Einstein's wildest dreams. One thing's certain: the night sky is about to become far stranger than we ever imagined. Stars don't just create light, they control it. Across the cosmos, these celestial furnaces don't burn in isolation. They shape their environments with winds and explosions so powerful they can stifle the birth of new stars before they even ignite. This self-regulation, called astrophysical feedback, is one of the universe's most fascinating balancing acts, and it might hold clues to why so much light seems to vanish from our observations. Picture a massive star shining millions of times brighter than our sun. Its radiation doesn't just illuminate, it carves. Ultraviolet photons blast outward like a cosmic pressure washer, stripping gas clouds of their raw material before they can collapse into new stars. When that star finally explodes as a supernova, the shockwave rips through neighboring nurseries, scattering potential stellar cradles into chaos. This feedback loop isn't just dramatic, it's essential. Without it, galaxies would burn through their fuel too quickly, creating stars in unsustainable bursts. But here's the puzzle: could this same process be dimming the universe more than we've accounted for? The numbers are striking. In starburst galaxies, regions where stars form at breakneck speeds, feedback can reduce star formation rates by half or more. That means entire generations of stars never get a chance to shine, their light effectively erased before it's born. Supermassive black holes add another layer to this cosmic thermostat. As they devour matter, they unleash jets of energy so intense they can heat surrounding gas to millions of degrees, preventing it from cooling and forming stars at all. The result: vast galactic regions that should be blazing with young stars instead glow faintly, their potential light locked away in hot, diffuse clouds. Yet feedback alone can't solve the missing light mystery. While it suppresses star formation, sophisticated simulations show it doesn't account for the staggering deficit we observe. There's another twist: feedback isn't just destructive, it's creative. The same supernova that disrupt star birth also forge heavy elements, enriching future generations of stars and planets. Their winds carve intricate bubbles and filaments in interstellar gas, structures that might focus or scatter light in ways we're only beginning to map. Some theorists suggest these processes could be redirecting photons rather than eliminating them, like a prism splitting sunlight into colors you didn't know were there. The deeper we look, the clearer it becomes. The universe's light budget isn't just about what's emitted, it's about what survives the journey. Feedback sculpts the pathways light travels, creating corridors where photons flow freely and shadows where they're absorbed or deflected. It's a reminder that the cosmos isn't static. It's a dynamic arena where stars and black holes wrestle over the very fabric of their galaxies. And somewhere in that chaos between the birth and suppression of suns lies a piece of the puzzle we've yet to fit into place. What's thrilling isn't just the science, it's the perspective shift. The missing light might not be lost at all. It could be transformed, redistributed, or lying in wait, hidden by the very processes that keep the universe in balance. Feedback doesn't just regulate stars, it challenges us to see the cosmos not as a collection of isolated lights, but as an interconnected web where every photon's fate is written in the dance of matter and energy. And that dance is far from over. What if the missing light isn't lost but leaking? The idea of a multiverse isn't just science fiction anymore. Theoretical physics paints a picture of our universe as one of many, like bubbles floating in an unimaginably vast cosmic foam. And if these parallel realms exist, they might not be entirely separate. Some models suggest the boundaries between universes could be porous, allowing energy, including light, to seep through. Imagine living in a house with thin walls, hearing whispers from the other side. Now replace the house with space-time, and the whispers with photons slipping into realities we'll never see. This isn't pure speculation. String theory, one of the most ambitious frameworks in physics, proposes that our universe might be a three-dimensional brane floating in a higher dimensional space. These branes could occasionally brush against one another, exchanging particles or even ripping open temporary bridges between worlds. Under the right conditions, light from our universe might cross over, vanishing from our observations without a trace. It's as if the cosmos has hidden trapdoors and photons are tumbling through them into the unknown. The math behind this idea is both elegant and mind-bending. In certain brane world scenarios, gravity, unlike light, can propagate freely between dimensions, which might explain why it feels so weak compared to other forces. If light occasionally follows gravity's lead, slipping into adjacent branes, it could account for the missing energy we've been chasing. Picture a flashlight beam shining against a wall with holes. Some light passes through, illuminating the other side, while the wall itself appears dimmer than it should. That's the eerie possibility we're facing. Our universe's light deficit might be someone else's illumination. Critics argue this is untestable, and for now, they're right. Without direct evidence of other universes, brane leakage remains a dazzling what if. But intriguingly, there are indirect ways to probe the idea. If light were escaping to other dimensions, it might leave subtle fingerprints in the cosmic microwave background, anomalous patterns or temperature fluctuations that defy conventional explanations. Some researchers even suggest that high-energy particle collisions, like those in the Large Hadron Collider, could produce signatures of extra dimensions, if only for a split second. So far, no smoking gun has appeared, but the search is far from over. What makes this theory so compelling isn't just its audacity, it's the way it reframes the mystery. The missing light might not be a problem to solve, but a clue to something grander, a cosmos far more interconnected than we ever imagined. If photons are slipping into other realities, it would mean our universe isn't a closed system. It's part of a vast, shimmering network where energy ebbs and flows across boundaries we can't even perceive. The most humbling thought, if light can leak out, something else might be leaking in. Those unexplained glimmers in deep space surveys, the anomalous energy signatures that crop up where they shouldn't, could they be photons from a neighboring brane, drifting into our universe like cosmic messages in bottles? For now, it's a tantalizing maybe, but in a puzzle as profound as the missing light, even the wildest ideas deserve a seat at the table. After all, the universe has never been shy about defying expectations. Why would it start now? We take for granted that the speed of light is constant, that a photon today travels the same distance in a second as one did 10 billion years ago. But what if that's not true? What if the universe's rulebook isn't written in permanent ink, but in pencil with constants that shift imperceptibly over cosmic time? This isn't just a thought experiment. Some physicists argue that fundamental forces like electromagnetism might have been stronger or weaker in the distant past, subtly altering how light interacts with matter. If so, the missing glow we've been searching for could be hiding in plain sight, its behavior warped by a universe where the laws themselves are in flux. The idea hinges on a radical rethinking of physics' most cherished assumptions. For centuries, we've treated constants like the speed of light or the fine structure constant, which governs how photons interact with electrons, as fixed pillars of reality. But when astronomers analyze light from quasars billions of light years away, they've spotted tantalizing anomalies. Certain absorption lines in that ancient light suggest the fine structure constant might have been slightly different in the early universe, as if the cosmos recalibrated its dials over time. The differences are minuscule, a fraction of a percent, but if real, the implications are staggering. Light from distant stars wouldn't just be redshifted by expansion. Its very properties could have morphed during its journey, making it behave in ways our modern equations don't predict. Here's where the missing light puzzle takes a surreal turn. If electromagnetism was stronger in the past, photons would have interacted more aggressively with interstellar gas, scattering or absorbing more readily than they do now. Over billions of years, this could have siphoned off vast amounts of starlight, like a filter gradually thickening across the cosmos. Alternatively, if the speed of light itself has slowed, a theory once floated to explain cosmic inflation, the energy of ancient photons might have decayed in transit, arriving fainter than expected. It's as if we're watching a movie where the projector's bulb dims scene by scene, but we've been assuming the brightness never changed. Critics counter that varying constants would leave other, more obvious fingerprints, like discordant measurements in nuclear decay rates or the cosmic microwave background. Yet the debate is far from settled. New studies of molecular clouds in distant galaxies are probing whether the electron-to-proton mass ratio, another supposed constant, might also drift over time. Meanwhile, lab experiments with ultra-precise atomic clocks have detected no variation in constants over a few years, but the real test lies in cosmological timescales, where even glacial shifts could compound into profound effects. The boldest twist, time-varying constants might not just explain missing light, they could redefine dark energy. If electromagnetism's strength is evolving, its influence on the vacuum of space might mimic the repulsive force we attribute to dark energy. Suddenly, two of cosmology's biggest mysteries could share a single, elegant solution. A universe where the rules themselves are written in starlight, slowly fading as the cosmos ages. What's humbling is the scale of the question. We're not just asking whether light disappeared, we're asking whether the universe's deepest laws are fluid, their permanence an illusion. Every photon we detect becomes a timestamp, carrying not just the history of stars, but the history of physics itself. And if those rules are shifting, the darkness above us isn't empty. It's a mirror reflecting back a cosmos far more restless and alive than we ever dared to imagine. Empty space isn't the barren void we imagine. It's a bubbling quantum sea, alive with particles flickering in and out of existence so quickly they defy detection. This quantum vacuum isn't just a backdrop for the cosmos. It's an active participant teeming with virtual particles that borrow energy from nothingness, exist for a fleeting instant, and then vanish back into the void. Normally, these particles are too ephemeral to leave a trace, But what if they're not just passive spectators? What if, on some imperceptible level, they're stealing light from the universe itself? Here's how it could work. According to quantum field theory, virtual particles aren't just mathematical abstractions, they're real enough to create measurable effects, like the Casimir force, which pulls two metal plates together in a vacuum due to the pressure of these fleeting particles. Now imagine a photon, a particle of light, traveling through this seething quantum foam. Every so often, it might interact with a virtual particle, transferring a tiny fraction of its energy into the vacuum. Individually, these losses would be insignificant, a drop in an ocean, but stretch that across billions of light years and trillions of photons, and suddenly, those drops could add up to a missing ocean of light. The challenge is proving it. Quantum vacuum interactions are notoriously subtle, operating on scales so small they're buried beneath the noise of ordinary physics. To even suggest that the vacuum absorbs light, we'd need to reconcile this idea with quantum electrodynamics, the wildly successful theory that describes how light and matter interact. So far, QED predicts that the vacuum should be transparent to light. Any absorption would be so negligible it's effectively zero. But cosmology keeps throwing us curveballs. If the vacuum is subtly siphoning off photons, it would require a tweak to our understanding of quantum fields, one where empty space isn't just a stage but an actor in the cosmic play. One tantalizing clue comes from the Casimir effect's darker cousin, dynamical Casimir radiation. In certain extreme conditions, like near a rapidly vibrating mirror or an accelerating black hole, the vacuum doesn't just subtly influence light, it can create it, pulling photons into existence from sheer nothingness. If the vacuum can generate light under the right circumstances, could it also do the reverse, swallowing photons under different conditions? Some theorists speculate that in regions of intense gravitational curvature, like near neutron stars or primordial black holes, the vacuum might behave differently, acting as a net absorber rather than a producer of light. Testing this would require experiments of almost unimaginable precision. Imagine trying to measure the evaporation of a single droplet of water in a thunderstorm. That's the scale of the challenge. Yet scientists are pushing forward. High-energy particle colliders probe the vacuum's properties by smashing particles together at near light speeds, searching for anomalies in energy conservation that might hint at missing photons. Meanwhile, astronomers study the light from distant quasars, looking for signs that certain wavelengths weaken more than expected over cosmic distances, as if the vacuum itself were filtering them out. The implications are staggering. If the quantum vacuum absorbs light, even minutely, it would mean that empty space isn't just an absence, it's a medium with its own rules, its own appetite. The darkness between stars might not be passive emptiness but an active participant in the universe's story, quietly shaping what we see and what we don't. And if that's true, the missing light isn't lost, it's transformed, woven into the fabric of space-time itself, waiting for us to learn how to read its new language. Cosmic shadows stretch across the universe like phantom mountains, sculpted not from rock but from pure gravity. When we peer into deep space, we're not just looking through empty darkness, we're gazing through a labyrinth of invisible structures so massive they warp the very fabric of reality around them. Galaxy clusters, those sprawling metropolises of stars, act as cosmic magnifying glasses, their immense gravity bending passing light like a prism distorts sunlight. This phenomenon, called gravitational lensing, can create surreal celestial mirages, distant galaxies stretched into glowing arcs, single quasars appearing as multiples, entire regions of space optically warped. But what if some of these gravitational behemoths don't just bend light? What if they swallow it whole? Consider the Bullet Cluster, one of the most studied cosmic collisions in the universe. When two galaxy clusters smash together at millions of miles per hour, their dark matter components revealed by gravitational lensing patterns plowed straight through the wreckage like ghosts passing through walls. The visible gas, on the other hand, collided and heated up, glowing fiercely in X-rays. This left a striking disconnect between where the mass actually was and where the light appeared. It's a perfect example of how cosmic structures can manipulate light in ways that defy intuition, not just magnifying or distorting, but potentially hiding it entirely. The mathematics behind this light-trapping potential is both elegant and startling. Any object with sufficient mass, whether a black hole, galaxy cluster, or something more exotic, creates a gravitational well so deep that light passing near it gets deflected. But at extreme thresholds, that deflection becomes so severe that photons get trapped in infinite orbits, never reaching our telescopes. While we know black holes create such light prisons with their event horizons, could larger structures achieve similar effects through collective gravity? Imagine a supercluster so vast and dense that its combined gravitational pull forms a sort of shadow zone, a region where background light gets bent away from Earth entirely, leaving what appears to be an unnatural void in our observations. Astronomers are already mapping these potential light thieves through ambitious surveys like the Dark Energy Survey and the upcoming Euclid space mission. By charting the distribution of galaxies and dark matter across billions of light years, these projects reveal where concentrations of mass might be redirecting or absorbing photons on colossal scales. Some intriguing candidates have emerged: colossal walls of galaxies spanning hundreds of millions of light years, vast cosmic voids where matter is suspiciously scarce, even peculiar cold spots in the cosmic microwave background that some theorists speculate could be shadows cast by superstructures beyond our current vision. The most tantalizing possibility: these shadow casters might not be made of ordinary matter at all. Certain exotic theories propose the existence of dark galaxies, structures dominated by dark matter with few or no stars to betray their presence. Others suggest topological defects from the early universe, like cosmic strings or domain walls, could create sharp gravitational gradients capable of shepherding light away like an invisible hand. If such entities exist, they'd be nearly impossible to detect directly, revealing themselves only through their light-blocking effects, like silhouettes projected onto the cosmic backdrop. What makes this hunt so revolutionary is how it flips traditional astronomy on its head. Instead of searching for light sources, we're learning to study darkness itself, to read the absences as carefully as the glows. Every unexplained shadow in our deep field images, every anomalous void in galaxy surveys, could be a clue pointing toward structures we've never imagined. The universe's missing light might not be lost at all. It could simply be waiting hidden behind cosmic curtains we're only now learning how to part. Our universe plays favorites. It overwhelmingly prefers matter over antimatter, and no one knows why. This cosmic bias, called Baryon asymmetry, is one of physics' deepest puzzles. For every billion particles of antimatter the Big Bang created, there were 1,000,000,001 particles of matter. That tiny difference is all that's left after matter and antimatter nearly annihilated each other in the universe's first moments. But here's the twist: that leftover matter now forms everything we see: stars, planets, even our own bodies, while antimatter has all but vanished. Could this fundamental imbalance hold clues to why so much light seems to be missing from our cosmic ledger? The connection isn't as far-fetched as it sounds. When matter and antimatter collide, they don't just vanish, they transform into pure energy, often in the form of gamma rays. This process is staggeringly efficient, converting mass to energy with 100% efficiency compared to nuclear fusion's meager 0.7% in stars. If pockets of antimatter still lurked in the modern universe, their annihilation with matter would produce unmistakable bursts of high-energy light. Yet when astronomers scan the skies for these telltale flashes, they come up empty. The cosmic antimatter hunt has turned into a ghost story with no tangible evidence of lost antimatter galaxies or stars. But suppose for a moment that antimatter does exist in some hidden form. Certain exotic theories suggest it might be sequestered in distant regions of space, separated from matter by domain walls, cosmic barriers formed during the universe's infancy. If photons pass through these antimatter domains, they could behave differently than in matter-rich space. Some models propose that antimatter might absorb specific wavelengths more aggressively, or that matter-antimatter boundaries could scatter light in unpredictable ways. It's like shining a flashlight through two different types of glass. The beam might emerge altered, dimmer, or even split in ways that defy expectations. The plot thickens when we consider antimatter's mirror image properties. While identical in mass to ordinary matter, antimatter particles carry opposite charges. This symmetry break could influence how light interacts with it. Laboratory experiments at CERN have shown that antihydrogen atoms absorb and emit light at the same wavelengths as regular hydrogen. But what if conditions in the early universe were different? Some speculative theories suggest that primordial antimatter might have interacted with light in ways we can't replicate today, perhaps leaving behind subtle imprints in the cosmic microwave background or creating voids where light was preferentially absorbed. Even without antimatter's direct involvement, baryon asymmetry's root cause might be entwined with our missing light. Many explanations for the matter-antimatter imbalance involve new particles or forces that violated symmetry in the young cosmos. These same phenomena could have also altered how light propagated, perhaps by creating temporary barriers that filtered certain photons or by generating exotic particles that absorbed starlight. The Sakharov condition's three requirements needed to explain baryon asymmetry include processes that violate both charge and parity symmetry. If such violations affected photons too, they might have left the universe's light budget permanently skewed. The most tantalizing possibility, that dark matter itself is somehow linked to this asymmetry. Some theories propose dark matter particles are relics from the era when matter first gained its edge over antimatter. If true, these particles might have unique interactions with light not just through gravity, but through subtle quantum effects that siphon off photons over cosmic timescales. It's a dizzying thought. The same process that filled the universe with galaxies and stars might also have set the stage for light to gradually vanish into the darkness. What makes this mystery so compelling is its scale. We're not just talking about a few dim stars, we're grappling with a fundamental imbalance written into the universe's blueprint, one that might have quietly shaped everything from the first galaxies to the light we see today. Every photon we detect carries echoes of that ancient asymmetry, a reminder that the cosmos has always played by rules we're still struggling to decode. And until we understand why matter won out over antimatter, we might be missing a crucial piece of the missing light puzzle, one hidden in plain sight since the very beginning. The mystery of the missing light isn't just a gap in our cosmic ledger, it's a doorway. Every time we think we've mapped the universe, it humbles us with a puzzle this vast, forcing us to question the very foundations of physics. Dark matter, black holes, hidden dimensions, these aren't just speculative ideas. They're the universe's way of nudging us toward deeper truths, reminding us that what we see is only a fraction of what's out there. The missing light could be the most important clue we've ever stumbled upon, a thread tugging us toward discoveries that might rewrite textbooks, consider how far we've come. A century ago, we didn't even know other galaxies existed. Now, we're grappling with the realization that the cosmos might be hiding entire categories of matter, energy, or even physical laws we've yet to name. The fact that we've noticed this deficit at all is a testament to human curiosity, the relentless drive to measure, question, and stare into the darkness until it gives up its secrets. And that's what makes this search so thrilling. It's not just about solving a puzzle, it's about the possibility that the answer might be stranger than anything we've dreamed up. Think about the tools we're building to chase this mystery. Telescopes that peer back to the universe's infancy, detectors buried deep underground, even quantum labs trying to recreate cosmic conditions, all united by one question: where did the light go? Every null result, every dead end is still progress. It's the scientific method at its finest, narrowing the possibilities until only the truth remains. And when that truth finally emerges, it won't just explain the missing photons. It could reveal an entirely new layer of reality, like pulling back a curtain to find a hidden room in a house you've lived in for years. So here's the beautiful irony: the darkness above us isn't empty. It's full of questions, and every one is an invitation to look deeper. Maybe the light isn't lost, just transformed, hidden, or waiting for us to develop the right tools to see it. That's the heart of science, not knowing but refusing to stop searching. And if history's any guide, the universe loves to surprise us. The next breakthrough might be lurking in data we've already collected, or it might require a leap of imagination no one's taken yet. Until then, keep wondering. The night sky isn't just a sight to behold, it's a challenge, a riddle written in photons and shadow, and you're part of the story. Every time you look up, you're joining a quest that stretches back to the first humans who ever wondered about the stars. Who knows, the answer to the missing light might change everything. And when it does, we'll be here to share it with you. Don't forget to subscribe so you don't miss the next chapter in this cosmic detective story. And drop your thoughts in the comments. What's your favorite theory about where the light went? The universe is